Hi, my name is Dave, and I'm developing a series of robotic challenges that will help students learn about coding and problem solving. I recently printed and assembled a simple line following robot for use in the line racer competition. This robot maneuvers using two wheels and has a pair of IR sensors mounted to the front of the chassis that allow it to follow a winding line. My next step is to program the robot using the Arduino coding environment. In this video, I'll demonstrate a C++ class that I created to help program the robot using a finite state machine. Finite state machines are wonderful programming devices that allow you to design and code complex mechanical behavior in a visual and intuitive manner. There are many variations on state machines. However, they all work by creating a network of interconnected states that the program transits in response to environmental cues. The type of state machine that I'll be using for my robot is known as a melee state machine because actions are implemented as the program transitions between states rather than in the states themselves. Let's go over to the Obsidian webpage, which I created for my state machine class, and I'll show you how it works. This C++ class essentially allows you to create a state machine in which the transition from one state to the next is triggered by a single Boolean event. Depending on whether the event is true or false, the program will transition from one of two events and execute various actions in the process, such as setting a timer or activating a servo motor. Although this is a simple mechanism, it can encode some complex behaviors. I'd like to use the example of a traffic light to demonstrate how I intend to design and program my robots using a state machine. The traffic light will periodically cycle between green, yellow, and red lights. Pressing a walk request button will prompt the traffic light to abort a green cycle and immediately signal the traffic to come to a stop. The first thing you need to do in designing a state machine is identify the actions that the robot will take to affect its environment. In the case of the traffic light, the device will either do nothing at all, set a timer for each of the light cycles, or turn each of the lights on or off. I've given each of these actions a 3-letter designator, which will make it easier to represent in the state diagram and resulting Arduino code. Next, we need to define the events that will cause the traffic light to transition from one state to the next. In this example, I've identified 5 Boolean events. These include timer alarms for each of the lights that will indicate when a light has been on for a required amount of time. There's also a walk request signal that is true whenever a pedestrian is pressing the walk request button. And finally, an always true event will be used to force the transition from one state to another. As with the actions, I've assigned 3-letter code to each of the 5 events. Now that we've identified all possible actions and events, we need to create a state diagram that shows how the events trigger actions and guide the transitions from one state to the next. Here's what a state machine might look like for our traffic light. Each state is represented by a box that contains a unique state number, in parentheses, and a coded Boolean event that will be used to trigger the transition from one state to another. The transitions are represented by 2 arrows. One arrow indicates the response that will be taken to a true event, and the other arrow shows what happens when a false event is detected. Each arrow also lists one or more actions that will be performed as the program moves between states. Notice that every state has 2 arrows coming out of it. Even if one of those arrows points right back to the state it started from, these return arrows are generally accompanied with a null action, indicating that the state machine does nothing during this transition. It's also important to point out that every state machine will start at state 0 and move forward from there. In our case, state 0 listens to the always true event and automatically proceeds directly to state 1. In the process, it turns on the green light and resets the green light timer. The traffic light will then oscillate between states 1 and 4 while it waits for either the green timer alarm or the walk request indicator to pop true and send the program to state 2. On the way to state 2, the traffic light will turn off the green light, activate the yellow light, and reset the yellow light timer. State 2 listens for the yellow timer alarm and moves to state 3, only when the alarm becomes true. During this transition, it turns off the yellow light, flips on the red light, and resets the red light timer. State 3 will listen for the red light timer alarm and send control back to state 1 when the event becomes true, switching on the green light and its timer in the process. That's it for the state diagram. So let's jump over to the Walkwe website, and I'll show you how I use the state machine class to convert this state diagram into an Arduino program. For those of you who aren't familiar with Walkwe, this is a free and absolutely amazing online tool that allows you to model an Arduino circuit and see how the code affects its performance. On the right side of the screen is my traffic light circuit, which connects 3 LEDs and a walk request button to the Arduino Nano. The left side of the screen shows the code that I created to implement the traffic light state machine, which we just discussed. I begin the script by including the state machine, timer, and sensor classes that are used in the program. All 3 of these classes are available here on Walkwe and on my Obsidian website. Next, I define identifiers for each of their Arduino pins that receive and transmit signals to the various peripherals. I also have a section to create each of the objects that will be used in this code. These include the state machine, red, yellow, and green timers, and the walk button. When setting up each of these timers, I give it a predefined countdown interval in milliseconds. Starting on line 18, I create action handles for each of the state machine actions and save them as integer constants. I do the same for event handles in lines 33 through 40. These handles come directly from the lists of actions and events that I identified when designing the state machine. In the setup portion of the script, I link each of the LEDs and the walk button to specific pins on the Arduino board. This is also where I construct the state machine by defining each of the states. The add state function accepts 6 state-specific parameters which indicate the number of the state and the event that the state uses to choose its exit path, the destination state and actions for a true event, and finally the destination state and actions for a false event. Note that when specifying multiple actions, you do so mathematically by adding the action handles together. This works because each action handle encodes a single bit and an integer number. The data for each state is easily compiled directly from the state diagram that we created earlier. Finally, the loop script cycles through 3 different sections that iteratively log events by retrieving Boolean values from the timer and button objects, call upon the state machine to evaluate and advance the state pointer based on these events, and finally implement any actions that the state machine is calling for by invoking functions associated with the LEDs and timer objects. When I press the play button, Walkwe compiles the code and runs it on a simulated circuit. As intended, the state machine iteratively activates the green, yellow, and red traffic lights. If you press the walk button while the green light is active, the program will immediately abort the green cycle and activate the yellow and red lights to stop traffic. And that's it. That's all there is to designing and coding a state machine on the Arduino. The great thing about using state machines is that they're visually intuitive, highly adaptable, and easy to troubleshoot by manually stepping through the diagram. They can also be built to encode far more complex behaviors than those I've shown here. You can also quickly sketch out state diagrams on paper, identify one that works for your application, and code it on the Arduino using the state machine class I presented here. In the coming weeks, I'll be using this state machine class to develop, test, and implement different functions in the Line Racer robot that I recently constructed. As I progress, I'll continue posting my code on the Obsidian website and documenting my efforts for these short videos. So please subscribe and follow along as I guide you through my process of developing and testing the Line Racer robot. Thanks for listening.